Pick one or two persons and make them turn red. Okay, so today I'm here to do a very basic introduction that's going to more or less lay out the framework for the validations, and then Doug Dreger is going to go over the interesting results from all this. So some of this is repetition from the workshop one, but I think it's important to understand the framework and the decisions that were made in designing the validation exercise. So there's a lot of people involved in this. I put a bunch of names down there, and there's even more. So it's a large collaborative effort using the SCEC, Southern California Earthquake Center. BPP is a broadband platform, and I'll go over the validation process. So introduction, motivation, you're all aware of it, but I'll go over it nonetheless quickly. Validation framework and schemes, we have a part A and a part B. The methods and input that are, I think, important to specify in here, and then how we see the results, and the evaluation tools that are produced on the platform. And I'll talk briefly about global evaluation process, because I know what Doug is going to talk about, and there's no overlap. Okay, so of course, this is a very large collaborative effort. There's a lot of people involved. We've been working really hard for over a year and a half. We have weekly calls and really a lot of work done all the time. And it's driven by the needs of seismic hazard projects, such as this one, SWOOS, for near-fault effects. It's really important. NG East is also very interested in that. As you may know, I'm a co-TI lead with Norm on this. And for the East, we don't have anything. Well, we have some data, but we don't have much data, so we need simulations. And also, this is going to be useful for the NG West 3, 4, 5, 6 projects. So this is done with the Southern California Earthquake Center, the broadband platform, and they had already developed a set of computational tools for ground motion simulations. And now we've really ramped up the post-processing and even the input-output of the design exercise you will see now. So this collaboration here is essential to success, so that's where I do my political spiel for my boss who's sitting in the room, that SWOOS, SCEC, and peer working together is the best thing in the world. Okay, so past validations. Let's hope it continues. Okay, he agrees. Okay, so past validations used to look like this, and I like to tease my friend Rob Grace because it's a figure from one of his papers, and that's not what we're after. So comparing simulated and recorded velocity traces is interesting, should keep on doing that, but this is really not what we're after. So what we want this time is a quantitative validation for forward simulations and engineering problems. So you see that the validation exercise is all, we thought it out as kind of a forward simulation problem, and then we use that to define the validation. Well, it'll make more sense in a bit. So short-term goal obviously is to supplement recorded data for development of GMPs and hazard analysis like this one, so especially near fault, hanging wall effects and things like that. Long-term goal globally is really we want to gain acceptance of simulations for engineering design. So given the focus here, we're only focusing on pseudo-spectral acceleration, 5% depth, and for a wide range of frequencies, so from 0.1 to 100 hertz, or 0.01 to 10 seconds in period. So we went through exercises like that, and I say we, it's mostly Norm, over the last few decades, and then me with NG East, and we encountered problems, and we thought we learned lessons, and we tried it didn't work. So the key from validation exercises, the key point here is you need more transparency. You cannot have one researcher working alone and coming up with the validation. So all the following points are, most of them target this issue here. So we need to validate against many events, not just have a model that works great for Loma Prieta, but doesn't work for Northridge or another region. So we've selected a lot of events, I'll show you that. We need a clear documentation of what are the fixed and optimized parameters from the modelers for each region. So we need rules from them, and that comes from really clear documentation on how to use their models and what is optimized for an event or a region versus what is rules that always apply. We need source descriptions are consistent between methods. And that's critical, because if everybody picks a different and source information, different magnitude, different geometry. We're not comparing apples to apples. So this is something we fixed in this. We picked a single magnitude and a lat long, length and downlip width, and we anchored those at a specific lat long, and all the models use the same definition. We also wanted to use a unique crustal structure, so that's VS, VP, QS, QP, rho, and all that for all the models. I'll talk a little bit about that. It's not always possible, but we want at least the models to use something that is consistent. So that is to prevent, well, again, we want to compare how the models behave under the same conditions. So we want to consider multiple source realizations. In the past, most people took an inverted source slip distribution and maybe a rise time distribution and all that, and then you run that through a model. Of course, that causes a problem of circular reference, and also because we're again thinking we're going to use those in a forward sense, let's do the validation thinking in a forward sense as well. So the only thing that is fixed is the hypocenter in some cases, in other cases not. And then we have the different models use their own source generators to create different realizations. We also had issues in the past when we asked people to provide results. As you know, ground motions are recorded on various site conditions, different VS30s, and some people didn't include that at all. Some people use linear models, some people use hybrid nonlinear models. Whatever, it didn't work out. So since we're interested only in PSA here, we said all the simulations are done for a fixed value, reference value, and we're going to apply corrections using well-calibrated site factors, empirical site factors, and correct the recordings PSA to that. So that's a critical difference here that in most cases. In the longer term, we hope to have good side effects modules in the broadband platform, but we're not there yet. So that's a workaround. We need to make all the validation metrics, computation tools, and plots in uniform units and format. It may seem obvious, but even if you clear the guidelines, all the plots are different scales, you don't know. So we've spent quite a bit of time implementing post-processing tools on the pipeline of the broadband platform. And also we need to tie it to a specific code, broadband platform version. Now it's anchored to version 13.6, for which the evaluation was done for all your work. NGEs, we're moving forward with the next version. So you know that your results are consistent with what was evaluated. So we have two validation schemes. The first one is more typical of what is done usually, validation against recorded earthquake ground motions. The second one is validation against GMP for generic scenarios. The part B here, we only do for Western US, for you guys. It's more to see that the models are giving about the right medians. We don't want to be off by a factor of 2 or more. So this is the idea. Through the validation process, the modelers have the opportunity to change some parameters and tweak and develop their rules, and we hope to keep continuing that with future versions, and so they can give clear guidance on how to use the model. So this validation exercise, I'm going to show you a flowchart here for both parts. So we start with events and stations. Basically we have OBS is observations, TS is time series, surface is surface conditions, okay, so as recorded. We use intensity measure processors, so that's to compute PSA, okay, and then we obtain observed intensity measures on surface conditions. We use the site factors, empirical site factors, to correct the PSA, and now we end up with observed intensity measures at the reference condition, okay. Then the simulations, they go straight and do the time series, so they obtain time series for reference conditions. They directly compute PSA, and then now we can compare these with what we call a goodness of fit, which is a residual analysis for reference site conditions, and that's what we're doing. So this part here is what we call part A, and that's done using past events. Part B, we create generic events here, and then we just compare the results with the simulations for those generic events from the GMPs. In part A, we also put all the different inputs here in GMPs, and we plot those as well. We'll look at that as well. As you'll see, it's useful because it gives us an idea of the repeatable event terms that are in the different scenarios. So, selection of events and stations, that was mostly done by Katie and Norm, I think. So we wanted a large data set here, so we have 23 earthquakes, covering many regions and tectonic environments, because we want to test the methods. Span a wide range of magnitude from 4.6 to 7.6, different types of mechanisms, and the selection was targeted to focus on well-recorded earthquakes. So there's 17 of them that have 40 or more stations. So then there was a whole very clever way of selecting a subset of stations. The target number was 40, and if you have questions, I have slides extra in the back to show how this was done. But basically, the subset of 40 was selected so that the ground motions were consistent with the whole data set, statistically. So those are highlighted in yellow here are the first 7 events that were selected. There had to be a choice because of time, resources, and technical issues. The evaluation that Doug will present is based on those 7 scenarios. 5 are from California and 2 are from Japan. And the idea here is we first started with avoiding complex structures and splay faults, and then cover a different range of magnitudes. I'll show you that in a bit. So the simulation methodologies that were considered, broadband methodologies that use full broadband Green's function wave propagation. There's 2 of those. There's University of Nevada, Reno composite source model, the UC Santa Barbara. Then there's stochastic methods, so those are based on some kind of a Bruin spectrum to start with. One that is not formally evaluated here as a point source, and we're focusing on finite fault simulations here, is the SMSIM. We used it kind of the same way as the GMPs, right? It's a point source, it's kind of similar to GMP anyways. It served as calibration, we looked at it, but it's not evaluated for this part of the project. And then XSIM is the finite fault version, or pendant, or I guess friend of SMSIM. Then we have hybrid methods that have been considered. So these use Green's functions at low frequencies and a stochastic method at high frequencies. The cutoff is 1 Hertz or 1 second. So Graves and Pitarka uses a sub-force spectra that kind of looks like what XSIM is doing, or SMSIM, underlying that. And San Diego State University uses the same low frequency Green's functions results as Graves and Pitarka, but they use scattering functions for the high frequencies. Those are the 5 methods that were considered. You already know which one's best because Jennifer told you. So input, again, the source is given the same for everyone. We had a consensus agreement on magnitude and size and dip and all that. For the Green's functions, for the path effects, I just had the slide here because we basically have a 1D velocity structures are defined. And for the low frequencies, this is used as is. And then the methods that use full broadband Green's functions had to make some adjustment because there are issues in using those Green's functions because of the reflectors not being placed in the right place and different interfaces that create issues. So they had an equivalent profile to that was slightly modified. And all of our profiles use a standard shallow velocity profile to our reference condition here, which is 863. And those who were there last time, remember it's 863.251. Anyway, so that all the models have the same reference condition. For stochastic methods, it's different. They don't use these velocity profiles. But they had to pick which empirical effective Q and effective GS, effective duration they could use. So they can't really do that. But for XSIM, they had to adjust the amplification factors, cross-hole factors, to match this, and they've done that. So the process, just to give an idea, for each scenario, we specify the source, magnitude, geometry, location, and for past events, the hypocenter is fixed. For the path, again, consistent with 1D velocity model I talked about. For site, we want to go from as recorded to reference, which is our 863. And for that, we use empirical site factors from Bohr et al. 2013 and GUS 2 prelim model that was almost final. That's what we use to do this. So for each scenario, you have seismograms for 50 source realizations, about 40 stations, 2 horizontal directions. So that's about 4,000 time series per event. So that's why we have such large numbers for Jennifer's simulations. Okay, evaluation products. So we care about PSA. We don't want to spend too much time on time series, but we want to make sure we don't have spikograms and these look like earthquakes. So we plot them as well. And they're all plotted. So this is an example of a recorded at 822 and the simulated was 863 VS30. We looked at those. Nothing crazy here. We also look at the UCID plots and make sure the energy release is about right. But this is more as a check, and we don't really evaluate those, just flash through and, okay, reasonable, move on. So of course, if they're recorded here at the much lower or much higher velocity, the waveforms can't really be compared anyway, so that's why we don't spend too much time on that. It's the correction we apply is only in PSA, not in time series. So what we end up with is here you have the NR is the recorded for a given station, and the green is the simulated. We focus here on rod D50, that's the metric we're using. We still compute north-south and east-west. And you can see these two are in pretty good agreement, at least in linear scale. The shape is about right. The thing we have here that's quite important to consider is the red line here. Shows where the data is basically unreliable because of processing, because of the instrument, once we process it, you lose certain frequencies. So this, when we aggregate the data together, we basically remove those points, so we're not biased by something that looks right, that is actually meaningless. Okay, so what we do here, basically, the main metric is goodness of fit. So we take the log ratio of the observed over the simulated, and that gives us plots that look kind of like that. So here's a plot that shows the red line is the median, and it's actually a mean. The yellow band is a 90% confidence interval of the mean, and the cyan band is the standard deviation. So on this plot, you have this goodness of fit parameter, or just residual, versus period. And as you can see here, this is a pretty good match. But as we go to longer period and we start to drop some data, the confidence intervals get wider, and it tells us not to trust that fit too much. So on one plot like this is all the stations and one realization of all the stations. We have 50 realizations. So what we do is we aggregate those together. So this new beautiful pink plot, very girly, I had to say that, is really just you have different colors so you don't mix up the one realization with the 50. So the colors are different enough even for colorblind people. This is again the same statistics, except that here we have all the 2,000 40 stations times 50 realizations. Okay, so we look at that. And then we also plot the same metric, the goodness of fit with distance. What you have here is 8 panels of different periods from 0.01 to 5 seconds. And you have the ball that represents the mean, and then the range of the data. And it's, again, still the same goodness of fit. We can see in this example, there seems to be a trend. That's not desirable with distance. So if I didn't say it, this is distance on the x-axis. So this is also something we look at, and Doug will show how we actually computed values that are meaningful based on that. But we can also just look visually and have a feel for it. In order to see if there might be maybe systematic directivity effects, we also plot this goodness of fit in maps. It's hard to see here, but it's the same 8 periods as we had before. But we have the fault traces right here, and then it's a color code that tells us the misfit or the bias relative to the recorded data. So we have those as well. And it was really informative in interpreting what we saw in aggregated forms. So we also produce goodness of fit plots, similar to what you've seen before, for the NGA West 1 GMPs. So we have the 4 models here. And for SMSIM, that I'm not showing here, this allows us to see the event turns, but we can also compute, systematic deviations from the median model. And again, Doug will show how we use these to kind of remove the systematic trends and evaluate the methods. But this is kind of a check, and it allows us to verify if there's something systematic. All this is combined into these great tables. And now what we did with that is we took basically the statistics of all those different plots, and we put them in different period bins, distance bins, so close distance, events or magnitude bins. Since we only have 7 events, each event can have its own line, and by mechanism. And Doug will show some of that and how this is used. But this is the data we use to evaluate the methods formally. So now we move on to part B. Everything before was for part A, so based on scenario comparisons. So now we selected 3 scenarios to check against GMPs. So we looked at the statistics of the database that were the 2 databases that were used to develop NGA West 1 and West 2 models, and picked where the models were well constrained. We don't want to go and compare it with a GMP where we know nothing about what went into it. So where we had the most data was for magnitude 6.2 strike slip, 6.6 strike slip, and 6.6 reverse. And we have a lot of information at 20 and 50 kilometers. So we picked those 3 scenarios and made generic fault descriptions. We have the dip that goes with that as well, but I'm not going to burden you with those details. In this case, we still do 50 realizations of the source. But because we're not talking about a single event, but in the GMP there's multiple events, we allowed them to randomize the hypocenter on the surface. So it adds a little bit of variability, and you're not tying things just to one point. And then we also did all those simulations for 2 velocity models, the Northern California and Southern California velocity structures. So evaluation criteria, so what you see here, let's focus now on the black line, which is the median of the 4 NGA models, but the NGA West 1 models. And then what we did is we took the prelim versions of the West 2 and all the NGA West 1 models, picked the highest point at any period and the lowest point at any period, and then we define a parallel line, just defines the envelope. That added 15% to the maximum, remove 15% from the minimum, and that's the dashed lines you see. And we felt that with that, if the simulations are within those bands that are fairly wide, it's a factor of more than 2 in here, actually it's more than that, then we were confident the method was working. So what you see then, the box plots represent the methods themselves. So this is the Graves and Pitarka for a specific scenario. The red is the median, standard deviation, and then the range. Again, Norm, I think you mentioned that. We're not looking at variability at all. We're looking at median values. That's what we focus on. Still, it gives us an idea. This method, for example, for this scenario would pass. Everything is within the dashed lines. We stopped this comparison at 3 seconds, where we felt that the database is still sparse, and so it might well be that the simulations are knowing something that the GMPs don't. So we're not using that part to judge what's going on here. So that's part B. So a quick summary of what we looked at. Those blue events are California events. I thought I'd show you what kind of magnitude distance range we sampled in there. Those are the events we used. Then we have the 2 Japanese events, and then we have the GMP scenarios. We actually have 3 scenarios that are kind of all lumped into those 4 points here. And that's the distribution of what we're looking here. So evaluation, big picture, before Doug gets to the juicy, fun stuff. So we asked all the modelers to provide documentation, detailed documentation, and the rules on how to use their model. So most modelers went and updated previous publications with changes they've made recently. And also they were to give us a self-assessment of where they expect their method to work. And so based on the technical basis, I'm not going to say who that is, but it's pretty much, yeah, this method is great. So it's just an example. But they provided us with their self-assessment, and then the review panel looked at it. So then the evaluation committee took that. So we evaluated the developer's self-assessment and requested justification. Or why do you think you can go to 8? Or why do you think there's a problem at low magnitude, and things like that. And then the evaluation committee also evaluated then the goodness of fit for part A and part B. That's really what Doug's going to talk about. But key here is that PSA is a controlling factor. And we have various numerical criteria that he's going to go over. And then we came up with a verdict for each of the methodologies. And this applies to now, the state of the broadband platform as it was in June. And the verdict is then, it's applicable now for a given region, distance range, bandwidth, and things like that. Are there limitations? And maybe the method needs refinement. It doesn't mean that we stop with that method. We keep on the development phase of the platform. So here are my references, and that's it.
Right on time.
Man, I'm good. So just before I go, here, this question will be easier to answer after Doug's presentation. So is what we've done, is it still relevant with the West 2?